Welcome to today's paper reading. Today's paper is titled, To CoT or Not to CoT? Chain of Thought Helps Mainly on Math and Symbolic Reasoning. This paper, published on the AR14 preprint, explores the effectiveness of chain of thought prompting in large language models, particularly focusing on its benefits in math and symbolic reasoning tasks. The authors, including Zayne, Sprague, and colleagues from the University of Texas at Austin, conducted a comprehensive analysis to determine the impact of CoT on various tasks. The study investigates the effectiveness of chain of thought (CoT) prompting in large language models (LLMs). CoT primarily enhances performance on tasks involving math or logic, with minimal benefits on other types of tasks. On the MMLU benchmark, CoT and direct answer methods yield nearly identical accuracy unless an equals sign is involved, indicating the need for symbolic operations. The analysis reveals that while CoT improves symbolic execution, it does not outperform dedicated symbolic solvers. These findings suggest that CoT can be selectively applied to maintain performance while reducing inference costs. Additionally, the study calls for new paradigms that better utilize intermediate computations across various LLM applications, moving beyond the current prompt-based CoT approach. Figure 1 presents a meta-analysis of chain of thought (CoT) literature on the left, where each point represents the delta of CoT over direct answering for various LLM task pairs. On the right, it shows the average performance of using zero-shot CoT versus direct answer prompts across 5 general reasoning categories, encompassing 20 datasets evaluated by 14 LLMs. The results consistently highlight that math and other kinds of symbolic reasoning tasks experience substantial improvements from CoT. The red dotted line signifies the mean improvement from CoT across all experiments. Notably, CoT demonstrates minimal gains on tasks that do not involve symbolic reasoning. The introduction of this paper discusses chain of thought (CoT), a widely used prompting technique for language models. CoT is known for providing human-readable explanations of problem-solving processes and enhancing the ability of large language models, LLMs, to answer complex questions through intermediate computation. However, the effectiveness of CoT is most heavily explored in the domain of mathematical reasoning, where it is often evaluated in a narrow slice of the task space. The paper aims to systematically evaluate where and why prompt-based CoT helps by conducting a meta-analysis of recent literature and augmenting this with experiments on 20 datasets and 14 contemporary LLMs across zero-shot and few-shot prompt settings. In this section, we define the tasks as consisting of a question queue within a vocabulary sigma and an answer within a label set LQ. LQ can include various data types or problem-specific labels. We explore 2 main reasoning strategies, direct answers and chain of thought (CoT). Direct answers involve a simple string realization of the answer, while CoT includes a sequence of reasoning steps leading to the answer. Additionally, we categorize problems into symbolic and non-symbolic based on whether they can be grounded in a formal system. Symbolic problems like 12 times 4 foot have a clear mathematical grounding, whereas non-symbolic problems like where to hold a cup to catch water on a sunny day lack a natural, agreed-upon framework. We also discuss the spectrum of reasoning, including semi-symbolic datasets like MUSR, which combine formal systems with common-sense reasoning. The meta-analysis involved filtering 4,642 papers down to 516 that mentioned CoT, and further narrowing to 110 papers that compared CoT prompting with direct prompting. This resulted in 1,218 experimental comparisons across 264 datasets, categorized into 14 task types. The most significant benefits from CoT were observed in symbolic reasoning, math, and logical reasoning tasks, with average improvements of 14.2, 12.3, and 6.9 respectively. While most benefits were seen in math-related tasks, some non-math datasets also showed notable improvements with CoT. Table 1 categorizes experimental comparisons into several key types, focusing on tasks that involve symbolic and algorithmic processes, mathematical reasoning, and logical reasoning. These categories help in understanding the types of tasks where chain of thought (CoT) prompting has been applied and compared against direct prompting methods. The table provides a concise overview of these categories, with detailed descriptions available in Appendix D. Figure 2 presents the results of our meta-analysis, showing the distribution of CoT deltas across various task types categorized in the literature. The data is aggregated by paper and category, indicated by blue dots, revealing trends across different papers. Notably, the categories that benefited the most from CoT are symbolic reasoning, math, and logical reasoning, with average improvements of 14.2, 12.3, and 6.9 respectively. The average performance on these top three tasks with CoT was 56.9, compared to 45.5 without CoT. For other categories, the average performance with CoT was 56.8 versus 56.1 without CoT, indicating a small but not significant improvement. Table 2 provides an overview of the models, datasets, and prompting strategies utilized in the experiments. The models listed include Llama 2 7B Chat, Mistral 7B Instruct version 0.3, and Gemma 2 9B IT, among others. These models are run with specific context size windows, with some limitations noted for the VLLM support. The datasets include Common Sense QA, Strategy QA, and GSM-8K, among others, each with specific characteristics and settings. The prompting strategies employed are zero-shot direct answer, zero-shot CoT, and few-shot direct answer, which are crucial for the experimental setup and performance evaluation. The experimental results indicate that chain of thought, CoT, significantly improves performance on datasets requiring math and symbolic reasoning. For instance, on the math dataset, CoT yields a 41.6% performance gain, and on GSM-8K, the gain is as high as 66.9%. In contrast, on non-symbolic reasoning datasets such as CSQA, Pika, and Wino Grande, there is little to no improvement observed with CoT. Additionally, the format of the answers does not significantly impact where CoT will help. However, free response capabilities may be slightly hindered by the need for pre-planning or reasoning about the correct response. Multiple choice datasets show similar performance with or without CoT. Figure 3 illustrates the performance gains from using chain of thought, CoT, across different reasoning categories. On the left, it shows the average CoT performance improvement for each reasoning category. On the right, it displays the performance gain for each dataset, averaged across models and broken out across 5 representative models. Red lines indicate median improvement. The consistent trend observed is that most improvements from using CoT are in math and symbolic reasoning, with math and GSM-8K showing significant gains of 41.6% and 66.9%, respectively. Semi-symbolic datasets also show moderate gains, reflecting the application of logical rules to reach answers. Table 3 highlights the top 3 slices that benefit the most from chain of thought, CoT, across MMLU and MMLU Pro datasets for Llama 3.18b and 70b models. Notably, 6 out of the 12 top slices directly involve math or mathematics. This suggests that the questions leading to improvements in other categories also have a mathematical nature. The table provides detailed performance metrics showing the error reduction percentages for each subject. Figure 4 illustrates the differences in performance between MMLU and MMLU Pro when a question or generated response contains an equal sign, with smiley face, or not, without smiley face. The figure highlights that CoT primarily aids in questions and responses that include an equal sign, which typically signifies math-related inquiries. This suggests that CoT is particularly effective for mathematical questions, with minimal impact on non-mathematical queries. Figure 5 illustrates different prompt variants designed to separate planning and execution stages for the GSM-8K dataset. These variants involve prompting a large language model, LLM, to initially generate a Python program as a solution plan. The Plan plus Direct Solver variant prompts the LLM to directly provide an answer based on the generated plan. The Plan plus CoT Solver variant prompts the LLM to solve the plan step by step with chain of thought, CoT, reasoning before giving an answer. Lastly, the Plan plus Tool Solver variant involves feeding the generated plan into a Python interpreter for execution. The chain of thought CoT method demonstrates strengths in enhancing symbolic reasoning tasks, particularly when it involves tracing and computation. This is evident in settings where CoT is paired with a solver, such as the Plan plus CoT solver, which shows significant performance improvements over direct answers. However, CoT's effectiveness is limited by the language model's ability to execute and track steps accurately. In most scenarios, CoT is outperformed by Plan plus Tool Solver, which uses external symbolic solvers. This suggests that while CoT can be a useful tool, it is a poor approximation compared to dedicated solvers. The evaluation results highlight that for tasks requiring substantial computation, pairing language models with symbolic solvers yields the best performance. This approach is particularly beneficial for math-heavy datasets, where the combination of LLMs with solvers consistently outperforms both direct answers and CoT methods. Figure 6 illustrates the performance of different prompt variants that separate planning and execution stages for math and logical reasoning datasets. It shows that while chain of thought CoT outperforms direct answer methods in solving formal plans and deriving final answers, it is still limited in its ability to perform symbolic computations. Notably, there is a substantial performance boost observed when using a combination of planning and tool-based solvers, Plan plus Tool Solver, over both CoT and a combination of planning and CoT solvers, Plan plus CoT Solver, across various models. This suggests that while CoT is effective, leveraging external symbolic solvers can significantly enhance performance in these tasks. The discussion highlights the benefits of chain of thought CoT in improving performance on math and logic tasks, aligning with early work on CoT for large language models. CoT's application has broadened to tasks not traditionally requiring multiple steps, often yielding small improvements over direct answering. However, a clear separation exists between performance on non-symbolic and symbolic tasks. The primary benefit of CoT is its ability to execute symbolic steps and track their output. Long horizon planning tasks, where symbolic reasoning helps substantially, have not been thoroughly covered in our experiments. There is a debate on the effectiveness of CoT in planning problems, with complex systems developed to improve planning. The potential for further improvement of CoT is explored, with evidence suggesting that additional calls to large language models can help, though this increases computation. Recent methods showing benefits from internalizing CoT indicate that explicit generation of intermediate tokens may not be fully utilized. In this study, the authors characterized the performance of chain of thought CoT through a meta-analysis and experiments across various models, datasets, and prompts. They find that CoT predominantly aids in math and formal logic tasks, regardless of whether examples are included in the prompt, the format of the questions, or the strength of the models used. Further analysis reveals that the majority of the performance improvement is consistently attributed to tracing the intermediate steps of a problem, a task for which symbolic solvers are better suited. Consequently, CoT rarely outperforms these solvers. The authors suggest that while CoT remains a powerful technique, future research should explore new paradigms such as search, interacting agents, or better fine-tuned models to enhance performance across a wider range of NLP tasks. In terms of reproducibility, the authors provide detailed information on how models were evaluated on each dataset. This is outlined in Section 4.1 and Appendix A. Additionally, all prompts used for each dataset, including model outputs and sampling parameters, are released on Hugging Face. For the meta-analysis of the literature, the filtering criteria and the process of annotating experiments into high-level categories are described in Section 3 and Appendix D. The full list of papers included in the meta-analysis, along with extracted experimental comparisons and task category annotations, is also made available. The authors acknowledge George Tsoukalas for his insightful feedback throughout the project, as well as Kai Bostrom and Usol Choi for reviewing and providing feedback on drafts of the work. Financial support for this research was provided by the NSF Career Awards, the NSF AI Institute for Foundations of Machine Learning, the Sloan Foundation, and Open Philanthropy. Thank you for watching.